Chemical kinetics, why does it matter? Why should we actually know about these things? Back to late 18th century, human created the first fertilizer, ammonia. People encounter a problem. Yes, we can generate those things, but the speed is actually very slow. How we can make these things go faster? So chemical kinetics has become a very popular science back to that time. But before we can learn all those knowledges, there are a few terms we need to define. The first term we need to define is the reaction rate. The rate was defined as the change of certain property over a certain time. The one easy example is actually the speed of a car. We know the speed of car is calculated through the change of distance over a certain amount of time. If there's a car travel 25 miles in 0.5 hours, then you know the average speed will simply be the change of distance is 25 miles, time is 0.5 hours, right? So we know the speed is actually 50 miles per hour. But if you put this concept into chemical reaction, it will become slightly different because the things we care about when we do reaction is the concentration. From that perspective, you will see that, okay, the delta Q, that Q will be replaced with concentration. T is still the same, so delta concentration, delta T, that will be the definition of chemical reaction rate. So in other words, what's the unit of your chemical reaction rate? It will be typically molarity per second. So you see this chemical equation, right? H2 plus I2 forming 2HI. So we want to define the reaction rate. On the left-hand side of the arrow, so we call this species as reactant, and this we call it as product. So now to express the reaction rate of these reactions, you can describe the reaction rate using the disappearing rate of your reactants or the formation rate of your product. Either way should actually give you the same information. However, if you actually look at these things, you will see the problem immediately. The example we're going to give you is actually assuming today, initially, you have 1 mole of H2, 1 mole of I2 for your reactant. You don't have any product in the beginning. Then you let the reaction to occur. After 100 seconds, you left with 0.5 H2, 0.5 mole of I2, and 1 mole of HI. So that's the initial and the end, and the time span is 100 seconds. If you calculate the disappearing rate of these reactants, we know the way you calculate it will be the final concentration of your H2 minus the initial concentration of H2 divided by delta T, right? The final is actually 0.5, initial is actually 1. And then you spend 100 seconds. Therefore, you get 0.005 molarity per second. And the fact that you have this negative sign is because this species is actually disappearing. The disappearing rate of your H2 is this much. For your I2, you can do the same calculation, right? You know your I2 final is, again, 0.5. Initial is 1. Time is 100 seconds. So under this case, you know it's also going to give you minus 0.005 concentration per second. What is the final concentration of your HI? 1, right? What is the initial concentration? Time span? Okay, so what's the number you get? It's positive, first of all. That means actually the formation rate, right? And then it's 0.01 concentration per second. After you calculate these things, you got 3 numbers. Minus 0.05, minus 0.005, and then 0.01. Which one you need to use to define your reaction rate? You can see if the coefficient is not 1 in your equations, it will become problematic because every species have different numbers. But you want to have one single number to describe the reaction rate. So how do scientists resolve this? What they do is this. They define the reaction rate is going to equals to the disappearing rate of your reactant multiply a negative sign. So like the overall reaction rate is always positive. In order to make every single species report the same reaction rate, you need to divide the rate of each species by its stoichiometry numbers. So what I meant by that is that 1 H2 plus 1 I2, they produce 2 HI, right? For each species, there's a stoichiometry number associated with it. So you can see for the H2 and I2, you got this coefficient of 1. But for your HI, you got a coefficient of 2. So we define the reaction rate is going to equals to the disappearing rate of your reactant divided by its coefficient. Okay, because it's 1, so even though I roll this, it's equivalent to just this, right? And to do the same thing for the others, it's delta I2, delta T, okay, but you divide it by the coefficient 1. Then it's going to equals to the formation rate of your product, which is delta HI, delta T, but you divide by the coefficient 2 here. Once you do this correction using the coefficient, then you're going to get a single number. Previously, we say this is actually 0.005, right? This is actually 0.01. If you divide this number by half, then everybody will be the same. To generalize this idea, let's say if we have A plus B, they give you C. A and B are reactants, C are products. So the reaction rate is going to be defined as the disappearing rate of your reactants, so delta A, delta T, and then normalized by the coefficient A. And it should equals to this and equals to this. This will be the general expressions. If you have chemical reactions, that's how you're going to calculate the overall reaction rate. Every time when they say the reaction rate is this guy. But if let's say I want to know the disappearing rate of A, then that's what I mean. If let's say I want to know the appearing rate of C, then that's the thing they want. So you need to actually have a clear distinction between different terms, so you can actually provide the correct answer. Here, just give you another example. 2NO2 is going to decompose to 2NO plus O2. So here, what is your reactant? NO2, right? What is your product? Every time you see an equation, make sure you know who are the reactants, who are the products. And then once you see those things, okay, then you should know the overall reaction rate is actually equivalent to the disappearing rate of your reactants normalized by the stoichiometry numbers. And it also equals to the formation rate of your product divided by its coefficient. So with that concept in mind, let's talk about how do we actually get this delta N2, delta T. Experimentally, what we do is like this. This is actually my reactant, and these two are my product. Initially, I just put these things in the container. Then I let the reaction to go on. Then I start to measure the concentration of this, and this. So you know at the time 0, you only have your reactants, you don't have any product. After 50 seconds, you check it again. Then you can determine the concentration of each species. Then you can repeat this process until 400 seconds. So once you are done with this, the next thing you do is you use your Excel to plot out those data points. NO2 is our reactant, right? So if you plot out the dots, okay, it will appear here, 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 and here. And then you can also plot out the same data for your products. This guy is actually for your NO, and then this guy is actually for your O2. So once you finish all these data collections, the next thing you do is to fit those data. That's why you see this nice curve. So from here, then you calculate the rate at any time point. For example, you can use this. That's your delta T. Then that's your delta N. Then this over this, they will give you the average reaction rate. So let's see how you visualize the reaction rates on the curve. The rate we'll calculate here is so-called the average rate, because you measure for extensive amount of time, right? So each time step is 50 seconds. So think about this. If say you make the measurement much shorter, at any points you can actually also calculate the rate. And those kind of rate is so-called the instantaneous rate. We are going to use this concept later on, but that's pretty much all the things you need to know on this plot. So if you go to the next slide, for a chemical reaction, 4NO2 plus O2 become to N2O5. If known N2O5 formation rate is 0.048 m per second, Write the rate expression in terms of the disappearance of NO2 and O2 and the formation of N2O5. And then you want to calculate what is O2 disappearance rate, what is NO2 disappearance rate, and what is the overall reaction rate. The question looks very complicated, okay, but it is not. The way you do it is just write down. I know the reaction rate is going to equals to the disappearance rate of NO2 negative, and then write out the coefficient. That should equals to delta O2 delta T. That should equals to your delta N2O5 delta T divided by 2. If I see this keyword, disappearance rate or the reaction rate, then I know I can always write down my overall rate equation based on the chemical equation I have. So let's actually, the first step, you should actually write down with this concept, and let's read carefully again. It says if it's known the N2O5 formation rate is 0.048. So N2O5 formation rate is delta N2O5 delta T. This is going to equals to, from there you know that is the things that you know. The things that you want to solve is EXU. Write down the O2 disappearance rate, right? That means I want to know delta O2 delta T. How do you get delta O2 delta T? Because you know this equals to each other. So since you know this, you can just solve that. So we know delta O2 delta T, we know is going to equals to negative 1/2 delta N2O5 delta T. That's actually negative 1/2 times 0.048. That gives you a number of negative 0.024. Now, third, what is the NO2 disappearance rate? So only one is actually this guy, delta NO2 delta T. And then you know this is equal to that. This should be 4 times delta N2O5 delta T. That's equals to negative 4. That's actually coefficient 1/2, okay. Okay, so it's 2 times 0.048 equals to negative 0.096. So what you really use is the equation you write out in the beginning, okay, and then plug in this and solve all the other terms. The final one, what is the overall reaction rate? You use this connected to that. Your overall reaction rate is going to equals to 1/2 delta N2O5 delta T. That's 1/2 times 0.048. That's 0.024 molarity per second. The key is that when you look at one equation, can you write out the general expression of the overall reaction rate law? And then based on the information provided in your equations, it will either give you this, or that. It will give you one of that, then you can calculate all the others. Okay, so this slide simply just tell you how the measurement has changed in the past 20 years. In old times, when I say in old times, like 19th century, when we measure all these kinetics, what you do is you cook your reactants, then you collect the gas, then measure the volume of the gas, then use your ideal gas to calculate the number of mole of your gas. That process is going to take very long, and then the accuracy is going to be relatively low. So nowadays, the state-of-art technology is so-called the stop flow experiment. So it works like this. In the beginning, you have reactant species put in a syringe. For example, you have reactant 1, reactant 2. They are going to inject the reactant into a small vessel, and then it will mix quickly. Once they mix, the reaction starts to occur. To probe the concentration of each species, we use something called the spectrometer. So spectrometer is an instrument that actually measure the fingerprint of your chemicals. So this way we can quantify the concentration of each species in very high accuracy. I think in the past 20 years, this has actually become the working horse to study the chemical kinetics. So nothing special, just to let you know what is the state-of-art technology we are using right now.